Okay, so today again we're going to continue the binary tree problem from the LeetCode. Okay, so today we are going to solve subtree of another tree. Okay, so I'll try. I have planned to do something new today. Like I will try to solve the problem in 30 minutes by myself. If I am not able to solve, then I will be going through the solution and then trying to solve again. Okay, so let's start the time. Given a root of two binary tree, binary tree root and subroot, return the true if there is a subtree of a root with a same structure and a node value of subroot, and false otherwise. Okay, a subtree of a binary tree is a tree that consists of nodes in a tree and all of this node descendant. The tree could also be considered as a subtree of itself. Okay, a tree could also be considered as a subtree of itself. Okay, so as we did in previous problem, to see if both are the same tree, we can do same thing again here. Okay, so what are the constraints? Constraint are, okay, the number of nodes in a root tree is in the range of 1 to 20. Okay, so there is no null node. Okay, the number of a node in a subtree is in the range of 1 to 1000. Okay, that is also not null node. So root value can be from negative 10 to the power 4 to positive 10 to the power 4, and subtree value also is the same. Okay, so let's continue. Okay, so what we are going to do is like like so what we are going to do is we start from the tree in which we are going to find start from the tree from which we are going to start them in which the subtree belongs. Okay, so start from the root and check if this root is equal to this. No, then we move on. Then again from using DFS we move on. Okay, so we again check this belongs to this. Okay, if both are same, then we again check its left and its left are the same. Okay, then again it's right and right are the same. Okay, so we do this if all the element from the subtree belongs to the tree. Okay, then we can return true. Okay, so basically what we're going to do is check the element from main tree to subtree until we find the root of subtree in main tree. Once we find the root of subtree in main tree, then we will start to check if all the elements of the subtree are same as all the elements in the main tree. Okay, so let's begin. Okay, so we have root tree and subtree. So let's start. First, let's check if so both are not null. So we can see it from the constraint. So what we're going to do is check if a root value is equal sub root valve. Okay, if it's true. If it's not true, what we're going to do is just move along the route. Okay, so what we're going to do is return route. What we're going to do is move along the root element. Okay, so is sub tree root left subtree. Okay, and each subtree root right from subroot. Okay, subroot. Okay, so we did this. Now what we're going to do is we'll create a variable here. Let's name it is this bool. It's sub okay. By default it will be false. So what we're going to do is sub equal to, we're going to create another function. Check, let's name check. So check sub, check sub tree. Okay, let's check sub tree. So let's check sub tree. Let's check subtree. In that, what we're going to pass in whatever the root is, and whatever the sub root is. Okay, so now let's create another function that will return bool check sub tree. Okay, so that will take tree node as a root, within tree node as a sub root. Now let's do the same as we did in the last problem. Check if 2, 3 are similar. Okay, so instead if these and these are the same subtree, so what we're going to do is, in this case, like we can 1, 2, 3, so we check this one, then this one, then this one. If there is no subroot and we have checked and everything has matched, we'll return true. Okay, so how we can do this is check. Okay, yeah, we have already checked if root valve is equal to root valve. So let's instead of doing this, let's check. We know that both are not null, so we don't need to worry about that. Then what else? We check if both are not null. Then again, let's check if. But now instead of checking if it's equals, let's check opposite. If root valve, okay, root valve, if it is not equal to root sub root valve, let's return false. Okay, else return check subtree, return the root left and subroot left. Okay, and let's check again. Right, for right, okay, check sub free root right, right, and sub root let's check it's sub root right. Okay, so we check, we're saying passing here, we're checking if it's this is that. Now check dollar, just we check this one, then we check this one, then we'll go down. If both root equal null pointer and sub root equals null pointer, then we return okay true. But there is a problem here, like let's we check this. What we do is here we will see the problem. Let's say we have now this subtree and this subtree, but we have one more like this one. Let's say we have one more here too. Okay, so we have one more here too, one more here as a 0. So what we did is we check if this equal this. Okay, so we just now we check this equal this. Okay, that's again true, then there is null and there is null. So what we do is we check null, both are null. Okay, that's return true. Then what we do is we go ahead check this equal this. Okay, let's return this is also return true. Then we will go in again. If this left is null, but current this is not null. Okay, this is not null, so this will return if root if main tree is not null but subtree is null. If main tree equals not null and subtree equals null, then what we do need to do is return false. Okay, but no, this if another is still return true. Okay, but okay, let's return true. Let's say there is another one here, but there is not here. Here it is null, but there is another value, let's say 5. What will now, after checking this, if main tree is not null but subtree is null, what we're gonna do is still return true, because okay. But if subtree is not null but main tree equal null, that means the element from this does not exist in this. Okay, so we return false. Okay, so basically if main tree is not null but the element of this is null, still will return true. Okay, no problem. Again, if we check this, it's null, but there is an element in subtree which does not correspond to the element in main tree, we return false. Okay, so basically if all the element in subtree corresponds to the elements in main tree, we return true. If any element of subtree does not correspond to the elements in a main tree, we return false. Okay, so as simple as this. Okay, so we have one condition: if both are true, we return true. Again, if root equals equal null, that is the condition. If root is equal to not equals to null pointer, and sub root equals null pointer, all we do is with the same element we just return true. Okay, but if root equals equal null pointer and sub root does not equals to null pointer, we return false. Okay, so these are the conditions that needs to be checked every iteration and return. Okay, so if this is for this to run, the condition, both of the condition needs to be true and both of the condition needs to be true. So what we're going to do is return is sub. So we need to return it's sub here. Okay, etur return it's sub. One second. If we never go, if we never find any of the element that's equal to this, what it is, we return tu and return it's sub. If we just return false, let's say for some condition here is 4 and here is also 4, but we check this, when we check it's false, instead of returning here it's not returning. For 4 that will return false. Instead of returning false here, we go in, then we check again for 4. We check this 4 and 4. Okay, both are same. So what we do is it goes inside, we check all the condition. No, so we come back. Okay, let's try it on this. Everything is, it's sub tree. Sorry, sub tree. Okay. If root valve equal subroot valve, member access with null pointer of check if this is equal to this. No. Then again we checked this equal to this subroot. Member access within a null pointer of tree node. Okay. Why is that happening? Root valve, subroot valve. And if root equal null pointer, then what it does is, if no element in subtree is to be found in a main tree is to be found in subtree, what we just do is return false. Okay. But if we do this, it will always return false. It will never return condition. So after checking the condition, whatever the condition we get, okay, we need to return this. So just return it's sub. Okay. Okay. Expected true return false. This is also false because so for some reason we are just returning false. For both the condition we are returning false for some reason. Oh, sorry. We need to make it a global variable so that we don't assign it in every iteration to be false. Okay? Now we are getting the first condition as a output. So in second condition we need to do false, but it's returning true. For 1, 2. For 5. So it is same as this one, so we return true. If it is, this is also 412, it is the subtree of this. Four, 5, 415. Okay, if subtree, the leaf node, if any node is even there, so return false. So instead of returning here true, so return It's false. Okay. Okay. Let's try submitting this one. Okay, we're getting an error in this problem. Expected true but returning false. Okay, no problem. So what we need to do is, so as you understand in previous one, even 412 and 412 are the same. There is a two sub node, but there is no two sub node, so returning false. Okay. Before I thought if even in any position, well, every exact same how it ends, the ending should be the same. Okay. So now let's see. We have written as 1 1 1 1. So we have 1 1 1 1 1 1 2 3 4 5 6 7 8 9. Okay. And we have 1 1 1 1 2 3 4 5 6 2. So 2 1. Okay, it is. It's on the right side. Okay, 1 2 3 4 5 6. So this is the same. So what we are doing is we're checking the sub for the first value. We went in, we checked, we returned false. Okay, that's okay. Number can be repeated. Okay, so we checked for 1, returned false, and we went with this again. We checked, this never became true. It's returned. So this return false. This std. Sorry, not here. Let's add. Let's see how many times it's getting colored. So it's getting called 1 2 3 4 5 6 7 8 9 10 11. 1 2 3 4 5 6 7 8 9 10 11. So at the end again, just if it's sharp, if it is true, even at any position, let's return. So let's return it. So now we are able to do, if any time, let's return this. So again, let's try to submit. Let's see if all the test cases pass. Again, for wrong answer. subroot 29. This is 29. So what we are doing is expected subroot, but I'm not null. Okay, this is one there. If this is not equal to this, okay, this is equal to this, so this returns true. No, this is false, whereas this should return. Uh, 29, 29, 29, 29. So this should return false. We know that for the subtree to be the last element, so the last element will this should return true. Okay, let's check if it has this, but it does not have plugin. If you go here, both left, we do is what we are doing is checking. So both are not null, then we're checking. So both are not null. This is also false. This is also false. So go here, check. This is also for the node left, left. So this will be true. So this will be true. We are checking it once, twice, once, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 28 times. Yes, our timer has finished. Right? So let's reset the timer. Let's go through the solution. Okay. So let's go through the solution. We know that we have to do this. So this is okay, fine. Let's put in the ChatGPT and find out what's incorrect. Right? ChatGPT. Cellular tools is closed, but there is a couple of important issue causing an incorrect behavior. Globally, its service is risky. It persists across recursive call and can be later wrong. Later wrong recursive function can so return. Okay, so instead of doing this, so let's remove this. If this happens, let's return false. Let's test this. Okay, so instead of doing this, let's do if let's return if this is true, let's return true. If it's never returning true, let's return false. It's returning false. We don't care whatever this returns. We care whatever this is returning. You are not using return value of the recursive call. This call are made, but the result are ignored. Unnecessary traversal even after match is found. Once you find a valid tree, you can immediately return true. That I did. That's what I did. Okay, they have removed this. They are not checking. They're checking sub condition for all the possible condition. Okay, checking sub root for all the possible roots and returning. Okay, so this returns true, then we go back, then we keep on doing this. That's why that's the reason. Okay. Let's do this instead of returning. Okay, so that was the error. So that what was happening, I was returning true, but I was not doing anything with the result. So what was happening, even once the result was true, it was returning false. Okay, so recursively it's like a little complicated to understand what is getting returned and what is not. So okay, let's go through the videos. So that's again, so we said this. So this is right. This what I got in this, if both are true, we return true. Okay, but in this subtree, even if we found once, if even once that we return true, we will return true. Okay, that I was not able to get grasp. I was thinking if I return true, it will get true, but I am returning true in a recursive sense. Even this is returning true in my code previously. Before returning, we are not doing, at the end we are returning false. So that was the problem. Okay, so I need to do more recursive problems, okay, to understand more clearly. Recursive, okay, or backtracking, those kind of problems. Yeah,
Hey everyone, welcome back, and let's write.
Okay, I haven't charged my earbuds, so I'm going to use the different one. Let's try this one again. Not working.
Some more NeetCode today. So today let's solve the problem subtree of another tree. And this problem is actually from the blind.
I need earphone, okay.
.75 list that we haven't really visited in quite a while because we've solved most of the problems on this list, but you can see one of the problems, one of the few problems that we missed was subtree of another tree. So let's solve that today. By the way, this
We also have notes for these things. Okay? So this is nice. Let's save this happen. It's normally docs. Okay. Excel open document. Excel. Okay, let's move on.
Is a spreadsheet we created a long time ago, basically just tracking all 75 of the problems in the blind 75 list. You can see I've taken some of my notes on each of these problems over here, and each of the problems, or at least most
Notes, about the notes, I take notes first. I try to solve the problems, then I try to forget it, then while revising I try to take notes. So I have a book somewhere which I write notes. Okay, it's there.
of the problems have a video solution that I created, and you can see about 16 people are actually looking at this sheet right now. I assume most of them are viewers of mine. And if you don't really care for spreadsheets, I actually did make a video playlist of each of the solutions. We have about 68 of them done. So pretty much every problem has been solved except for just a few of them, most of the hard problems at least. Okay, now let's get back to the problem. The description of the problem is pretty simple. We're given two binary trees. One is called root, so this is that entire tree, and the second tree is called subroot, and this is that second tree. And the only thing we want to know is this subroot, this tree, this entire tree, is it a subtree of this tree on the left? Is this one a subtree of this one? Now, first question, what is a subtree? So for this root tree, what's a subtree? Basically, you can start at any node in the tree and then take all of the nodes in that subtree, right? So for starting at 4, this is a subtree of the tree. Starting at 1, the node itself is a subtree. This itself is a subtree. This itself is a subtree. Even starting at the root node, this entire tree is a subtree of itself. So now the first thought that you probably have is to check if this is a subtree of this tree, let's just brute force it, right? And how would that work? Well, basically we would check, visit every single node in the root tree and then check, starting from here, does the tree match the subroot tree? So let's start at the root, right? The root of both of the trees, 3 and 4. Are the root values the same? Well, they're not, right? So that kind of automatically means that this entire tree is not equal to this tree. So then we continue, right? We check, okay, starting from here, starting from the 4, are these two trees the same? Well, we check the root value. They're both the same. They're both 4. So at this point, we're basically just comparing these trees to check if they are equal. And we can do that recursively. There's actually another LeetCode problem called same tree that I would recommend solving before this problem if you struggle with this problem. This one is also an easy problem if you want to check it out. But yeah, we can recursively compare these two subtrees. 4 and 4 are exactly the same. So now let's check the left child of both trees. 1 and 1 are both the same. Now let's check the right child. 2 and 2 are both the same. So yeah, these subtrees, this tree is a subtree of this tree because we did find a subtree that matches this tree. So I think this is one of the problems where the solution is actually really simple, right? For every single node in this tree, let's call it S. For every single node in this tree, we compared that subtree to this entire tree. Let's call this tree T. So the way the worst case is going to work out, basically for every position in the S tree, we'd have to end up going through every single node in the T tree, right? So from here, let's say this was a 4, the worst case would be that we'd compare all 3 nodes with all 3 nodes here. But of course we didn't have to do that because the root nodes weren't the same. But what I'm getting at is basically the overall time complexity for this solution, the brute force, is going to be S times T. And yeah, this works. So basically the size of both trees multiplied together. So this will get us accepted on LeetCode. But just because understanding the solution is simple, it doesn't mean implementing it is simple. It's actually kind of tricky. And my suggestion to you would be, since this is a tree problem, most tree problems are easiest to understand when you think of them recursively. So let's try to do that. Initially, the problem is we want to know, is T, this subtree, is it a subtree of the entire tree here, right? Is it a subtree of this tree? To determine that, the first thing we did was checked the first subtree, right? The root subtree that matches this tree, right? So just 3 nodes in this case, right? And we found that no, this subtree is not the same as this one, right? And by the way, to check that comparison, we could create a helper function to do that for us. We'll call it same tree, right? That'll be a helper function just to compare 2 trees to let us know if they're equal. But in this case, it didn't work. Right, so now we have to continue the problem. And like I said, let's think of this recursively. Initially, we wanted to know, is T a subtree of this entire tree? We found that it's definitely not if we start at the root. So now let's ask the subproblem, is T a subtree of the left subtree of...
So even still, if you think, if it's true, we return true. So for this, if check return true, we are returning true, so it is getting true, but still we keep on getting inside this to see. Okay, this will return true, this will return false, they both return true, again keep on returning true. Okay, but even once I want to return true, but no, does not want to get more deep, into the tree, because we return true, but if the tree is bigger, we keep on getting we keep on checking still to get false and true, false, true, and getting true. We don't want to do that. Okay, so what can but still we are not checking if we're not even going inside this, so that's not the problem, but still we are going to the loop checking if it's true. Like if we found on the left side, listen, if we find this as a true and return true, we still check this, we're still checking if 5 and 4 are the same, even if it's we have returned true. So okay,
the root node. And when I say, is it a subtree of the left subtree over here? I'm not asking, is it the same tree? I'm asking, is it a subtree? So we're going to have 2 functions in this case. One is the helper function same tree, and another is going to be another function. I don't know what it's going to be called. I think it's just the generic function that they give us. I think it's called is subtree. So basically that's how it's going to work. Is subtree is initially going to be called with S and T. Is T a subtree of S? Well, we'll check, is it the same tree first, right? Okay, it's not the same tree as S. So then we want to know, is it a subtree of the left subtree? So what are we going to do in that case? Well, we're going to call the same tree function. Is it the same tree as the left subtree? So that's the main idea, but I think it won't make 100% sense until we actually jump into the code. So let's do that in a moment. But as with most recursive problems, we definitely don't want to forget about the important edge cases when we are comparing the trees. So first thing, let's start with the helper function. What would happen if both trees were null? In that case, are they the same tree if they're both null? And yeah, if both trees are null, yes, they are the same. What about if 2 trees like this one and this one had the same initial values, right? Like the first 3 values we can see are the same, but what if one of the trees had an extra node here, right? Then is this tree the same as this one? Of course not, right? So we'll have to keep track of that when we do.
Not just in subtree. If we have extra node in subtree, or even in a root tree, if there is another element here, I will return false. Okay,
our is same tree function. Now, what about the is subtree recursive function? If both of these trees are null, is our is subtree going to return true? Is t a null subtree, a subtree of another null tree? Well, that's going to depend on our same tree helper function, and it's going to return true. So yes, a null subtree is a subtree of another null subtree. But the more interesting edge case is, what if S was null, right? S is empty, but T is non-empty. In that case, is T a subtree of this one? Nope, it's not, right? Because this tree cannot be found anywhere in the S tree. But what if the opposite was true? What if T was an empty tree? Then is an empty tree a null tree? Is it a subtree of a non-empty tree? And in this case, the answer is yes. And the main intuition I use is basically, if we had a null tree here, we could just go to one of the children of, one of the leaf children of the other tree, and technically these have a null subtree because they do have a null child. So that's kind of the intuition I use. But that might be a good clarification question to ask in a real.
But you can see in the constraint given in the LeetCode problem, we can be sure that there will be at least one root node and at least one subroot. Otherwise, if it was not true, we should have added more edge cases here. Okay, so we already have given the constraint, we don't have to do this. Okay, so let's
interview, but in LeetCode's case, I think they do want that to be true. So those are the main topics that I wanted to go over. So now let's actually jump into the code and see how we can implement the solution. Okay, so now let's get into the code. And like I said, we are going to find one more function.
So we have already implemented this sim solution here. Okay, so we have implemented the solution here, and we have implemented in C++. He's going to implement in Python. So let's I will explain this again, okay, once again for you guys to understand, if anyone is watching. Okay, so first what we do is check if the root is null. If a root is null, we return false. But this is not just to check if the root is null, this is to check if the leaf, if you go to the leaf node, like if we go to the leaf node and return its left from here, it will return false. Okay, then we check if when we are recursively calling, check if the root node and subroot node values are same. If they are same, we are checking check subtree. Okay, we are checking check subtree function. So checking the subtree. In the subtree, what condition we need to check? If both are null. If both are null, we are returning true. If one is null and another isn't null, we return false. If this is null, this is not null, still we return false. So if any of one is null and another isn't null, we return false. So we can do this in one line, I think. Okay, what can I do is, if root instead of doing this, we can do is, we can do and if root equal null or subroot root equal null. If any of these is null, if both are null, return true. If any one of these is null, like let's say, or let's comment this one. Okay, let's run this. We return false. Okay, so that's it. It's equal null. Okay, you can see still no problem. We are getting the solution. Okay, so let's move on. Okay, so let's move on to the next problem. Okay. What is the next problem? Now we went to the medium level problem for the tree, binary tree. So let's open this one. So what's the problem? Let's start the timer again, once again. Okay. Timer will lowest common ancestor of a binary search tree. Okay, given a binary search tree BST, find the lowest common ancestor LCA node of two given node in BST. Find the lowest common ancestor node of two given node in BST. According to the definition, one of the definition of LAC, lowest common ancestor on Wikipedia, the lowest common ancestor is defined between two nodes P and Q as the lowest node in T that can be both P and Q as a descendant. The lowest common ancestor is defined between two nodes P and Q. Okay, between two nodes P and Q as the lowest node is T. As the lowest node is as a lowest node in T that has both P and Q as a descendant. We also allow our node to be descendant of itself. Okay, so let's go through the example to understand the problem nicely. Okay, so this is the given BST. Okay, binary search tree. Okay, so this is the given binary search tree. We are given P and Q, that is 2 and 8. So output is 6. So LAC of 2 node 2 and 8 is 6. And 2 and 4 output is 2. The LAC of node 2 and 4 is 2 since a node can be descendant of itself according to the LAC definition. And 2. So basically what we need to do is instead of DFS we need to do BFS and check if a node with P and Q, so if the node with P and Q are child of any node, okay, basically. So or if P and Q are either child or itself, okay. So return. Okay, so what we do is we need to do this problem into breadth first search. Okay, we need to create a queue. So let's take this, add it here, don't save. Okay, let's what is the problem given? Okay, so we have P and Q. What we need to check what we need to check is if P and Q are child of any node. Okay, like let's say P is 2 and Q is 8. So 2 and 8 is child of 6, so we need to return 6. Okay, and again there is one thing said in the definition that let's say if P is 2 and Q is 4, so here if we check in this subtree, okay, in this subtree 4 is the child of 2 but 2 itself is in that 2 is as a parent, so this can be true. Okay, as you can read, where we allow a node to be a descendant of itself. Okay, so there is, if we check in this subtree, parent, left child and right child both are same. 2 4 are in this subtree, we have 2 and 4. If there is 2 and 4, we return child parent node. So basically, if you think it simply, what we need to do is, take a parent node, child node and its left child, see if any three of these elements include between P and Q. If it is, we return parent. Okay, so all we need to do is take 6, 2 and 8, check if P and Q belongs in this belongs in it. If it does, we return parent. Okay, so let's do this. Where condition, we take node, its left child, right child, compare it to the, like, what will take this, its left child and right child, compare it to P and Q and C. Okay, so what we can do is, we can even use hash map to check. Okay, so what we are going to do is take a root node, take its left child and right child, add it to hash map. Okay, then check if P and Q belongs in that hash map. If it does, return true. Okay, so we can do this left child, right child, then this, then again this. We can do DFS2. Okay, in this problem, what we'll do is, we check for this node, left child, right child, add it to the hash map, check PQ, then again clear the hash map, check for this one, then again go check for this one, then check for this one. Okay, so what we are going to do is create a DFS. Okay, first our condition is most important problem. Let's go to the constraint. So the number of node in the tree is range from 2 to 10 to the power 4, so we don't need to worry about that. Okay, so values are this, all node value are unique. Okay, that is, and P is not equal to Q, that is also true. P and Q will exist in BST. Okay, will exist. Okay, it's sure it exists. Okay, so what we are basically simply is going to do is, first our problem is to take a root node, its left child and right child value, add it to, no, first if we go here, if it is this, if we go to the leaf node, all we need to do is return if it is what to do if well, we will never reach the leaf node. Okay, if the condition is according to this, if P and Q will exist, will never. But let's say we go up to here, check if left and right, let's do this, let's add up, let's do a stack, like a stack. Okay, instead of doing it like a recursive, let's do in a stack. Okay, let's create a stack of 3 nodes, because if we do recursively, if we goes to the end of the node, we need to return something. This problem will return something which will not be true. So let's do non-recursively. Okay, so this first name stack, and let's dot push root. Now while stack is not empty, while stack is not empty, let's do let's pop the top element of the stack. Let's pop the top element of the stack, so that will be tree node. This tree as the top. Okay, now let's pop that element from the top. Okay, let's pop that element. Let's pop. Let's pop. Start pop. But okay, let's pop that element. Before let's implement a simple DFS. Okay, so what we will do is check if as t left is not null, then push as the push t left. Again check if t right is not null, then as the push t right. Okay, let's see. Now what we do is we do push but we need to do one more thing. We need to create a hash map. Let's create an unordered map of int. It is int, okay, it is it. So another map of int, as we have already in the constraint we have seen node value are unique. Okay, all value are unique, and p and q are never same. So what we're going to do is let's do m hash map as the m, unordered map as m. That's a hash map. Okay, so what we're going to do is push h m dot insert. What we are going to insert is top valve. We insert a top valve. Then what we do is insert if left is not null. Let's insert t left valve. Okay, in insert. Okay, let's do this. That's in that insert t right value. Okay, inserted its value. Now what I will do is check if p live stream underscore everything wants to streamize again. If let's check in hash map, that's m. Let's check in hash map. We find what we find q. If it is not null if it is not equal to HM.end. If this is also not equal to end, and HM that find again HM that find P. It is also not null. That means we need to return T. If both are null, let's return true. If it is null, all we need to do is clear the hash map. Let's end that clear the hash map. Okay, and let's move on to the problem. Okay. If both are not null, let's return true. We clear it also. We clear hash map so that we can insert it again. Okay. And else, if otherwise, let's return. Okay. For some reason, let's return. So there is an error. Hash map int, sorry. Instead of int, again that would be, instead of hash map, let's create a set, unordered set. And as we know, all the t values are unique. We don't need to worry about that. Okay, so being okay. So tag s. Let's send that insert. Q dot find is not equal to HM.end. Instead of HM, let's leave the as snap P dot find HM dot find. Okay, sorry, P and Q are nodes. We need to see its values are equal or its node are equal. We need to check its value or node. Let's check its values. Okay, value. Okay. Okay. Let's run this. We'll get an error. Okay, so what's the condition for an error? We need 1 and 4. 1 and 4. So expected 3. Okay, not in just subtree. In subtree. Okay, so I thought only in this left, right. I thought it current node, left node, and right node, but not if it exists anywhere inside it. It exists anywhere inside it. So what we do is we can do it instead of doing left, right. Then I am inserting this one, inserting this. Now we can do it recursively because we need to start from bottom. Let's check for this node. Let's add this node, then add this node and this node, then add this node. Now let's add this node and this node. Then we add this and this to hash map. Then again we add this to hash map. So what do we do? 5, 3, 6. Check if it exists inside. No, then wait. No. Then again what we do is we go inside 3, 4, 3, 4, 4, 2, added 1. So for node, for 2, we add 1. Left as well. So we need to return 2, but if we do this, if we don't clear it, it will be it will give. If we don't clear it, it will return 2. Actually it will return 2, but we need 3. If we don't clear it, so let's try it. What is the problem? So for 3, this 2 exists, but for 2 it does not exist. Instead of doing from top to bottom, we need to do from top to bottom. We need to do bottom to top. Okay. So this we have done top to bottom approach. We need to do bottom to top. So let's clear this one. Okay. Just do from bottom to top. So what we do is we keep on going inside the loop until we reach the null node. Okay, we add null node. And so we get to the null node, we add current node. This node. Again, we go, add this node. We go ahead, we add this node. And we add this node, then we add this node. While adding this node, we'll see. So once again, minutes ago, we have 6 minutes. So what's this? Let's do this. Simply what I do is, so if you root variable null root the null pointer, not root will not be null pointer. What it is, this need node, so we need to create another. I think we need to create another function in which we will go from top to bottom and return. Okay. What we can do is, if it is null pointer, first we check. We add this, then we add this, then we add this. Then we add this, then I add this, then add this. Let me check what we have here. Check this for this one. We add this. So simply what we can do, we need to do is bottom up approach. How we can go along with bottom up approach? If 620 allows customer ancestor, we send its left, then I can set it left, but now it's null. Left, okay. We went down. We went its left. We can check. Yeah, that is this. Then okay, so now for this test case, this particular test case, I am not able to, like, if I add this one first and this one, then if I add this one, then this one, then this one. If I add this one and check, then I add this one and check. How can I? Left. Null. Add this one. So this will reach there. It's here. After reaching here, we have already reached here. Then we will reach here. So we cannot do BFS, DFS, BFS. So we do this and this one. Let's check. Let's go through the solution, okay? Solution. And binary search tree and DFS. So for this problem, if we are checking it left, right, if current node, it's left node and right node, I have implemented the solution for that. But if we are going deep, then I am not able to think how to solve the problem. So let's go through the video, okay? So how to solve this problem.
Hey everyone, welcome back, and let's write some more neat code today. So today we're going to solve lowest common ancestor of a binary search tree. And if you recall, a while ago in a video, I showed you guys this sheet of the 75 blind problems that have become pretty popular. And so this is basically a spreadsheet that I showed with an entire list of those problems. And I've actually ended up making videos for most of these problems so far. The video that we're doing today is actually going to be lowest common ancestor, one of the few problems that I haven't done yet. So I will be linking this sheet in the description if you do want to take a look, and I'll probably be trying to wrap up most of the problems in this list. I think one of the next ones that I'm going to be doing is Alien Dictionary because I really like that problem. And once I've gotten this entire sheet of problems done, I'll probably be making a playlist for it. But for now, you can watch the videos that are currently available for this list of problems. So in this problem, we're given a binary search tree, and we're supposed to find the lowest common ancestor of two given input nodes in the binary search tree. And so the lowest common ancestor is basically defined as being the lowest node in the tree such that P and Q are descendants of this node, or P or Q happens to be equal to this node. So basically, what we're saying is 6 can technically be a descendant of itself. So for example, in this example, we're given P equals 2, Q equals 8. So we're going to start at the root because the root is always going to be a common ancestor of every single node in the tree, right? That's just kind of basic, right? For this node and this node, of course, this is going to be a common ancestor. It's not necessarily the lowest common ancestor, but it is a common ancestor. So what we're going to see is P is less than 6. Therefore, it's going to be in the left subtree, and it actually happens to be a direct child of 6. 8 happens to be greater than 6, so it's going to go in the right subtree.
Okay, so that's the binary search tree. I didn't know about binary search tree, right? I did not know if you have to check it, if the element greater, you need to check it in left or right.
Basically, if we went in the left subtree, 2, is 2 going to be a ancestor of 2 and 8? Of course not, right? 2 can't be an ancestor of the node 8 if it's in a different subtree. Similarly, 8 is not going to be a common ancestor of 2. So basically, if we look at this level or if we keep going down, we're never going to find a common ancestor between 2 and 8. So the lowest one that we found ended up being 6. So we notice if there's a split between the nodes that P and Q are going at, if they're going in separate subtrees, where that split occurs is going to be the lowest common ancestor. So if I change this problem slightly and I gave P as 7 and Q as 9, we would once again start at the root because we know this is going to be a common ancestor of these two nodes. And so now we're going to check, okay, 7 is greater than 6, right? And 9 is also greater than 6. So therefore, we don't need to search in separate subtrees. We can just go to the right subtree to look for both of these values. We know that this is not going to be the lowest common ancestor. This could potentially, though, be the lowest common ancestor. So now, once again, we're going to repeat that. We're going to say 7, that's going to be less than 8. So for a 7, we're going to have to look in the left subtree. 9 is greater than 8. So for that, we're going to have to look in the right subtree. So since this is where the split occurred, that means this is going to be the lowest common ancestor for this input. So we would return this node as the lowest common ancestor. So one last case is if we changed Q to be a 6. So once again, we would start at the root, right? Before we were checking if P and Q were both greater than 6, then we look in the right subtree. If they're both less than 6, then we look in the left subtree. If one of them is in the right subtree and one of them is in the left subtree, that's how we know this is the lowest common ancestor. But what about the last edge case where one of these nodes happens to be equal to the root node? In that case, this is potentially the lowest common ancestor. It's definitely a common ancestor of both of these, but now if we go lower, for sure none of the descendants of this node, nothing in the left subtree or in the right subtree is going to be an ancestor of this node itself, right? So basically, if we ever reach the node itself, for example 6, then that's going to be the lowest common ancestor. So it's an ancestor of itself, and it's also an ancestor of 7, which can be found down here, right? So this problem isn't too difficult once you can kind of understand that if there's a split between these two nodes, then that's going to be the LCA, the lowest common ancestor. And since we're doing it this way, we don't have to visit every single node in the entire tree. So the time complexity is not going to be big O of n, it's going to be log n, because we're only going to have to visit one node for every single level in the tree. So basically the time complexity is the height of the tree, which is usually going to be log n. And the memory complexity is just going to be big O of 1, because we're not really needing any data structures or anything like that. That being said, let's jump into the code now. So
Okay. Understanding the solution, you do this. You need to go to the root. Let's check if both root valve root valve is smaller than p. Okay. And root valve valve p valve is smaller than this number. This is greater than valve. So what we do is return root. Yeah. So if root b valve is greater than and valve is greater than sorry, if valve is greater than root valve and q valve is also greater than root valve, what is return step return what is common it's step also if both are greater both are the root left common q okay. Status if both is smaller and it's okay, so do right just right divided left both is smaller it's and now if e valve okay p is smaller than root valve then root and if it is not if root whether both valve will be equal to p valve or root valve equal to q valve return root let's return root. Every case we are getting root as an output so that's the problem. So if p valve so for the stage 2 and 4 if both p and q p valve is smaller than root valve and q valve is smaller than root valve what it now is root left p and q so this is happening comes here. It comes here. Now again, check 4, 2 and 4. Check it. If both is greater, no. If both is smaller, no. Check either. Check this, what do you call it? It's another foot. Then we check either RETU or understand. Okay, now what is happening? Basically, we go to the 6. We check if both are smaller, as both are smaller. So we go to 2. We again check if go to the 6. If both are smaller, no. If both are greater, no. If then we check if one is smaller and another one is greater. If one is smaller, P is smaller, and Q is greater, no. Then we check if any one of those is equal to S, then root. Then we return root. So this return root, then we return true. Okay. So this is the basic problem. Okay. So basically, this is how we solve this one. Okay. If you want to get this faster, there is all of those things. Function. Okay, so if instead of doing any of this, because in both cases we are returning root, we don't need to do this. Okay. In both cases, if we are returning root, we don't need to do that. Return root, okay. Okay. So that is fixed. What is happening? We keep on going, checking if both are smaller, we return this. If both are greater, we return this. If we go again side, if either one is smaller and one is greater, we need to return root. If any one of those is equal to root, we return a root. So we return root. We don't need to check. We don't have to do this. Don't need as okay. So as simple as this. Okay. Shift on this function, returning this. Or this will be the root. So we don't need to do this one. Okay. So that's it for now. From next day we'll try to solve other problems of tree. Okay. So that will be binary tree level or traversal and binary tree right side view. Okay. So that's
As
for
I
now.
mentioned. null because our current pointer to current dot. In case we can update current and set it equal to current dot left. Now the last case is basically if our split occurs or if we end up actually finding one of the values p, or would just be an efficient solution and execute at some point. So as you can see, this is a pretty efficient solution. So I hope that this was helpful. If it was, please like and subscribe. It supports the channel a lot, and I'll hopefully see you pretty soon. Thanks for watching.
Thank you for watching.